We're going to use the fact that logarithmic functions are inverses of exponential functions with the same base to come up with a graph of a logarithmic function. So first, I'm going to look at the graph of an exponential function. We've seen this already. This is something we know a little bit about. Taking a look at this is generic y equals 2 to the x. We know the domain of an exponential function is all real numbers. Negative infinity to infinity. I can use any x value that I want, any real number x that I want, and put it in there and get out a y value for 2 to the x. The range, on the other hand, of an exponential function, we said is only 0 to infinity, not including 0. If we look at the graph here, if I put in a really big negative value of x, I can get really, really close to 0, but I can't take a positive number and put an exponent on it and have it actually be equal to 0. So I can get as close to 0 as I want, but I'll never quite get there. On the other end, my graph goes up very fast, so I can get any positive y value that I want all the way up to infinity. So range 0 to infinity. And we said there's an important point, a y-intercept of 0, 1. Since any base to the 0 power gives me 1, that's an important point. And there's an asymptote, horizontal asymptote to the left. The negative x-axis is a horizontal asymptote with the equation y equals 0 to the left. So those are some things we already know about exponential functions. I would like to use that to come up with a graph for the function y equals log base 2 of x, the inverse of the exponential function with base 2. And you might remember that the graph of an inverse is the graph of the original function reflected over the line y equals x. Which means if there's a point x comma y on the original function, that's going to correspond to, if I flip-flop the coordinates, on the graph of the inverse. Well, we know a few points on the graph of y equals 2 to the x. First one is that y-intercept, 0, 1, is going to correspond to a point 1, 0 on the graph of the inverse. Since 2 to the first power is 2, I get the point 1, 2 on the graph of y equals 2 to the x, which will correspond to the point 2, 1 on the graph of the inverse. Since 2 to the second power is 4, I had a point 2, 4 on the graph of 2 to the x, which will correspond to the point 4, 2 on the graph of the inverse. If I go to the left, if x is negative 1, 2 to the negative 1 power is 1/2. So I have a point at negative 1, 1/2, which will correspond to the point 1/2, negative 1 on the graph of the inverse, which is about there. If I connect these dots, looks like I'm going up to the right, not real fast like the exponential function, but up. And then since the negative x-axis was an asymptote for my original function, that's going to correspond reflecting across the line y equals x. The negative y-axis will be an asymptote for the inverse for the logarithmic function. So the red one here is a graph of sort of your generic y equals log base 2 of x. Let's make some observations. You might remember, since x and y switch, the roles of x and y switch for the inverse, the domain and the range flip-flop, and that's consistent with what we can see on the graph. The domain of this logarithmic function is positive x values only, which is the range of the exponential function. Positive values only. I can't put a negative value into a logarithm and get out anything that makes sense. The range, I can get any y value that I want. This asymptote here, I can go to negative infinity really quick. To the right, my graph is always going up. It's not going up especially fast, but it's always going up. So I can get any positive y value that I want eventually. And my range is all real numbers. The point 0, 1 corresponds to the point 1, 0. So that's going to be important when we start doing transformations. And instead of a horizontal asymptote, I have a vertical asymptote going down the negative y-axis with the equation x equals 0. And there's my graph of a logarithmic function.